Good morning. My name is Gavin Bailey from Aimsun. I'm going to talk to you about traffic digital twins. Some of you who have attended previous calls would have been bored by me already. Hopefully I'm going to be presenting slightly different information or giving you some additional insights to previous presentations. So our interpretation of a traffic digital twin is a digital replica of road and pedestrian and cycling infrastructure connected to real-world sensors. These can be delivered at any scale, going from a junction and corridor all the way up to region and a national scale. It's important, I think, to mention here that the digital twins that I'm talking about are primarily deployed for management of traffic incidents on networks where current automations like urban traffic control and urban traffic management and control systems can't actually handle them. So there's actually already digital twins which have been deployed in the field for decades, which many of you may not be aware of. They try to make the green lights work better and in your favor. Many of you may disagree, but those are typically there to make micro adjustments to the traffic network to optimize the flow of traffic through the network. These systems are typically deployed where there's such a dramatic change to traffic flow on the network. We typically refer to them as incidents. That might just be congestion rather than an actual traffic accident, that adaptive control is unable to handle the situation, and you need to have another system kind of come in and intervene and then support, and then you can overlay that optimization on top of it. The way that we deploy traffic digital twins at Aimsun can differ. So visually they can look very much the same, and in some cases the use cases are very similar, but we deploy them primarily by two means: data-driven and simulation-driven. Now, the data-driven digital twins, they're real-time and they allow for identification of recurrent events, so it's really leaning on the benefits of AI. These are typically used for situational awareness and automated detection and management of recurrent events. Then we've got our simulation-driven digital twin, which uses AI layered on top of our traffic simulator. It's a piece of modeling software which has been in the market for about 30 years or so. And we use that to enable better prediction or simulation of what is likely to happen if you were to intervene. So it enables you to go beyond the limitations of AI. So just very briefly, when we start a digital twin, we as all digital twins need, we use a lot of data. This is detector data from the Manchester network. These are loops in the road which are used for adaptive control. So we're using the same data collection equipment which is out there, which is used for your adaptive traffic control systems for traffic signals. And we actually use AI techniques in a number of ways with this data. So as you can see, you've got the detectors down the left, down the side, and then a year's worth of data going out along the bottom. And you can see a lot of the detectors aren't working. They're not collecting data. That's represented in black, or they're sending poor data, which is in red, moving to green, which is your good data. And we'll actually use AI techniques to uplift that data, to interpolate and impute values on detectors which are sending bad or poor data. And it will do that by looking at surrounding detectors or data from that same detector, but where it's sending good data on another day. Then we'll use AI to derive meaningful insights from those detectors. So here we've actually extracted traffic patterns from the detectors. These are patterns used in the traffic industry to depict how the traffic behaves on a given day. And these are emergent patterns from the data, and then we can actually overlay those onto a calendar year, onto a calendar for the entire year, structured with your days of the week along the top. So you can see that Saturdays and Sundays, and actually Fridays in this case, are very clear in the data. And then you can see your seasonal variation in terms of the blocks of color along the bottom, horizontally. This is an example of a deployment that we've got of a data-driven digital twin in Spain on the C32. It's a toll road, and as you'll see here, we actually collect the data, the real-time data, and we can feed it into graphs. So you've got your trend map, and you've got an analytical prediction for how the traffic will behave over the coming hour. This data-driven digital twin is really only good for prediction of recurrent events on your traffic network. It can take data from point sources like your UTC detectors and also floating car data, which is presented there. When we predict the future, we also measure how good that prediction was when it actually becomes real time. That graph was from an early deployment, so that was this system's actually been in place for about year and a half now. When we typically deploy one of these systems, we get about 65-75% accuracy in terms of our predictions versus the reality when it actually arrives. If I were to be able to demo this system today live, you'd see that the predictions are coming in at about 80-90% accuracy. So as with an AI model, the longer it's deployed, the better its predictions become. So many of you who are working in digital twins at the moment will be kind of familiar with these limitations around AI. They require large sets of relevant data, training data, and the bigger the data set, the better. So then they become less sensitive to anomalies and errors within those within the data which are relevant to the trends which are present. It's only really suitable for areas or locations where you have measured things and those events have been observed. So it goes back to the point of they're not really as valuable to understand or to predict how non-recurrent events might behave or might the reality might kind of play out. So they're good for detecting incidents and anomalies, but they're not necessarily good for predicting the impacts. But that's where we can bring in simulation. And this is a video of a deployment that we got in Oxford. And here in this system, this actually allows an operator to go in and manage an event. They can identify the incident, and then they can simulate the impact of several strategies on that incident. This can simulate up to 4 strategies: 1, do nothing, and 3, do something. So you've got the do nothing up in the top left. And the operator can actually click through for the hour to see how the response plans play out. We've also got numerical and graphical representations to enable for quick decision making. And of course, if you integrate pre-established KPIs in this system, then you can actually fully automate this process and you can remove the human from the loop. But what we're seeing at the moment in these deployments is that people are understandably a little bit cautious about this. So they're retaining the human in the loop for the moment. But from this visual output, because it's a simulated incident, the do nothing is actually the most appropriate here. So it actually shows that no action is the best action. One of the most difficult things to communicate with these, and this plays to some of the speakers before me, is that it's very difficult to communicate the use cases or where these are useful and they can add value, because digital twins are a tool. They're not a specific thing which does just one thing well, certainly not in the context of traffic. So this is just kind of a demonstration of some of the case studies where we've deployed digital twins to show where we've responded to kind of the market in terms of their needs. So the San Diego model was actually one which we deployed in 2013. So we've been apparently building digital twins for quite some time. But we see them commonly applied in the UK context to your kind of standard transport policy goals, such as congestion management and network capacity, kind of safeguarding environmental performance, so your traffic-related emissions, and also more recently road safety. So these are quite a diverse tool, and it's that thing of trying to find use cases and find that kind of not just implement a digital twin for the sake of it, actually find a very key kind of specific functional requirement and then design it around that system around it. That's my presentation today. Thank you very much.
Gavin, question for you. Is there Aimsun system available for decision makers in real time, can you make informed decisions on road traffic events?
Yes, and yes. Aimsun systems are real-time. The two that I kind of showcased are real-time systems, and they're actually deployed in the UK and also internationally in many other countries. The decision-making tool which I showed on the Oxford model is actually a example of the decision support functionality, which is used for non-recurrent road traffic events. So the intention is that you can actually set up automations and also use a human user can use it to make better informed decisions about traffic management in real time.
Within digital twins for transport, are you working alongside the new mobility as a service apps, which are being rolled out across the UK and are helping drive people out of their cars and onto public transport?
So we're not working with mobility as a service companies because their business models are predicated on capturing that data and commercializing it and selling it. But we are working with local authorities to use their UTC data, so the traffic control data, and also floating car data providers like TomTom or Here Technologies, to improve the traffic network and improve things like bus reliability. So we've actually rolled out a system which will be live in Tees Valley in January next year, specifically purposed with improving bus reliability over an entire city or over an entire region, so that it makes more sustainable modes more attractive to users.
Brilliant, thank you. And you've listed a couple of companies there that you're working with, and similarly, I imagine companies in partnership, as one of our questions here is going to ask in a minute. But another question to both of you is, what is the best approach for big data analytics and decision making, considering the huge amount of data that you're collecting in your respective solutions? How are you tackling that?
I'll go first. Okay, so the best approach. Well, from our perspective, there's two types of, I've already referenced kind of two types of data. So the primary data that we use, the first is the urban traffic control data. And that the value in that data is that it's sometimes low coverage, but it's high fidelity. So you've got infrastructure in the road which captures 100% of the traffic going over it. So you have a full understanding of exactly what your traffic population is doing. The other kind of big data set which is available is your floating car data. So from TomTom and Here, which actually they're one of the biggest transport data providers that most people haven't heard of. Anyone who uses Spotify in this room, they're tracking you. We can use that data, but it's a sample, and we don't actually know what the sample rate is in any given part of the country unless we have the UTC data to then reference it. So it's finding the right blend of data and data types to then contextualize one another and extend the coverage. So floating car data gives you your higher coverage, but a lower sample, but it's a sample. Even Google, which is one of the best, only samples at somewhere between 3 and 40%. Anything above 10% in the transport industry is considered good. Whereas UTC data has poor coverage, but very high, it's the highest sample rate you'll get. So it's finding the blend, really.
The final question here, which you kind of touched on, but I'll ask it explicitly anyway, is do the cars that are surveying the roads need cameras to be added to them, or are they already in the vehicle? And are drivers aware that they are feeding data into the twin? And I guess that's to yourself, but also expanding on the various methods of which we are sampling people and their cars and how that's being done at the moment. So please.
Any data which we do actually work with is, if it's floating car data and tracking data, it's highly aggregated to the point at which it's impossible to identify a single person. And when it comes to UTC data, we're collecting two basic traffic characteristics, flow and count, over the detectors. They're literally inductive loops in the road that count your vehicle as it goes over it and tell us how many axles there are. So we know nothing about the actual individuals, which can be problematic and limits the future of digital twin technologies when it comes to agent-based models and activity-based models. But that's a whole nother issue.